We'll wait till 6:05 for other students to join, and if yeah, we'll wait till 6:05 and then we'll start. Am I audible to everyone? Last time there was a problem with the microphone. Hopefully this time it is better. Yeah, last time my earphones were not working properly, so I got new earphones this time. Similar to last week, I'll solve 10 problems. I'll tell you the method to solve the problems, and you can also check there's a video, problem solving session video from the professor itself, so you can check that. And along with this session, it should be enough to complete your assignments. Okay, the first question is, consider a 7 4. So code word length is 7, n is equal to 7, message length is 4, k is equal to 4. Linear code given by the parity check matrix H, and you are supposed to use the same matrix H for all three of the first three questions, and H is given by the following matrix: 1 0 0 1 0 1 1, that's the first row, 0 1 0 1 1 1 0, second row, and third row is 0 0 1 0 1 1 1. And the question is, what is the random error detecting capability of this code? So you have a 7 4 linear code with a parity check matrix as given. You have to find out how many errors can it detect, how many bit errors. So this is not error correcting capability, it is error detecting capability. I'll give you 2 minutes to work it out yourself and give you the solution after 2 minutes. First class, it's all right. First, so these are only problem solving sessions. I won't be teaching you any theory in this class. So, how you are supposed to go about this is first watch the lecture videos of the corresponding week. So, now we are in week 2. So, you have to watch the lecture videos. Then you can attend the problem solving session where I'll solve 10 problems, and these will be similar to your assignment questions. So, of course, they won't be the exact same thing, but they'll be similar enough such that using the concepts that I have used, maybe formulas or techniques, whatever is used here will be useful for completing this week's assignment. So, this week's assignment probably you have to submit next week, right? I am not sure about the dates. So, you can attend this session and it will be helpful for your assignment. Of course, if you have any doubt in the theory, also you can ask me, but not this week. This week I haven't prepared. But from next week, you can ask if you have any doubts from the lecture, and I'll be happy to help you with that also. Let's go ahead and solve this question now. So, the basic thing that you have to keep in mind is for a linear block code, the minimum distance, which we call d min, denoted by d min, is equal to the minimum number of columns of parity check matrix H that will add to a zero vector. So you have this matrix H. How many columns should you add to get a zero vector? What is the minimum number of columns that you should add? So if you take only a single column, there is no zero column in the parity check matrix. So with just a single column, you won't get the zero vector. Let's say you try with any two of these vectors. Let me try with these two columns. 1 1 0 plus 0 1 1, and the addition is in binary. I won't repeat that later. In the beginning I will remind you whenever it's necessary. So in binary, 1 plus 0 is just 1. 1 plus 1 is 1 0. So we'll take only the units place. So it's 0. 0 plus 1 is 1. This is not the 0 vector. Similarly, you can try to add any two of the columns and you won't get a 0 vector. That is, the any two columns are independent of each other. Now if you try the same thing with three columns, you could take the first column and the second column. The sum of those two columns, first and second column, will be 1 1 0. If you add that to the fourth column is also 1 1 0. So if you add these two columns, you will get 0 0 0. So by adding three columns, you can get the 0 vector, and that's the minimum number of columns you have to add. So that means those three columns are dependent. So minimum number of columns which are dependent. Now in this case that is 3, and that will be the minimum distance of your linear block code. So dmin is equal to 3. That's the first thing you need to find out. The other thing you need to know is, if the minimum distance of a code is dmin, a code with minimum distance dmin, you will be able to detect dmin minus 1 errors. Can detect dmin minus 1, which is this, in this case, is equal to 3 minus 1, which is 2 bit errors. So if you have a code word and you pass it through the channel, each code word will be of 7-bit length. Then if two of the bits get corrupted, so let's say you sent 1001 110, and some two bits got corrupted, they don't have to be adjacent. This and this are fine. If you receive 001 1110, then this particular code will be able to tell that an error has occurred. It might not be able to correct this error, but it will definitely know that an error has occurred. Okay, so the answer is two errors. Let's go to the next question. So in question 1, they asked us to use the same parity check matrix for question 1 to question 3. So you'll have to use the same parity check matrix for question 2 also. And question 2 is, if AI denotes the number of code words with Hamming weight I. So the Hamming weight of a code word is nothing but the number of ones that occur in the code word. So if you have a code word 1001100, there are 3 ones in this code word, so the Hamming weight of this code word is 3. AI is the number of code words that has Hamming weight I. Then find the weight distribution of the code. Which code? The code whose parity check matrix is given in Q1. So let me copy down this matrix first. I'll give you 2 minutes to solve it yourself. Okay, this is a lengthy question, so you won't be able to solve it in 2 minutes. Let me just give you the solution directly. I will give you the solution and you can stop me if you have any doubt. What happens to carry bits if we add 1 plus 1 plus 1? Nothing. Here we are not trying to. What we are trying to find is different, right? We just want to know how many columns we have to add to get a zero column. So the carry doesn't matter for us. In a computer, if you had to do 1 plus 1 plus 1, let's say you had a computer and you could only store 1 bit. Then when you do 1 plus 1 plus 1, it's actually 3, which is 1 1. Right? This 1 is carried over to the next bit and your answer is 1. It will store this 1 here and it will just discard the carry. There's no more memory. If you do have a memory, then it will, you can store the carry also. No, bits of the code word are not independent. They are very much dependent on each other. The way you get the code word is by taking linear combinations of the rows of the generator matrix, right? So if you have a message vector u, you multiply that with the generator matrix. So that will give you, if your u is some u1, u2 to uk, you'll have k rows. If the first row is g1, second row is g2, last row is gk, then the code word you will get is u1 g1 plus u2 g2 plus etc. So the bits of the code word depend on u1 u2 on the message. So you can't say that the bits of the code word are independent from one another. So the reason why we are finding the minimum number of columns that add to 0 and why that will give you d minimum, I explained it in the previous lecture. You can go and watch the recorded lecture of that on YouTube. The link should have been shared with you guys. Okay, we'll continue with question 2. So first we have to find out the Hamming weight of all the code words. That is the weight distribution is nothing but finding out the number of code words with Hamming weights for all possible Hamming weights. So any code word will have the zero code word. Any code will have the zero code word 000 whose Hamming weight is 0. You might also have the code word 11111. If there are n bits, the Hamming weight of that code word will be n. So from 0 to n you can have any number of any of the Hamming weights. And you might have any number of A0 will always be 1 because that's the only code word. 0000 is the only code word with Hamming weight 0. So this index is the Hamming weight. This is the number of code words that have that particular Hamming weight. So A0 is always 1, and then you have to find A1, A2, etc. up to AN. And in this case, there are 7 bits, so you have to find A0 to A7. And for that, you first need the code words. And the way you get the code words here, they have given you the parity check matrix. If you observe this, this is of the form IP. It's in systematic form. So from that, you can directly write your generator matrix. The generator matrix will be in the form P transpose I. So this part is your P and this part is your I. So the generator matrix for this code will be P transpose is 110 011 111 101 with I, the identity. That will be the generator matrix for the code. Then you can list down all the code words. The way you do it is you write down all the possible messages. Since it's a 7-4 code word, there will be 4 bits in the message, so 16 messages are possible. If the bits of the messages are U3, U2, U1, U0, they can take 16 different values. Twelve, 13, 14, 15. So 0 to 15. And then the code word corresponding to each of the message, you can get the code word by multiplying this message with G. So 000 times G will be, and let's so the next code word 0001 times G will be the last row 1010001. Next one will be the third row 1110010. For this you will have to add the third and the fourth row. So that will be 0100011, right? So in this way you'll have to write down all the 16 code words. All we are doing is we are taking the message and multiplying it with the matrix G, where the message is a row vector. The row vector times a matrix will give you another row vector. Okay, and then uh, I'll simply write down the code words. You can verify that yourself later. So these will be the code words, and then let's write down the Hamming weight of each of the code words. Weight, so the 0 code word has weight 0, the next code word has weight 3, this has weight 4, 3, 3, 4, 3, 4, 3, 4, 3, 4, 4, 3, 4, and 7. So now we can write down the weight distribution. Distribution will be A0, that is code words with Hamming weight 0, you have one of them. You don't have any code words with Hamming weight 1 or 2, so A1 and A2 will be 0. Number of code words with Hamming weight 3, 1, 2, 3, 4, 5, 6, 7. Number of code words with Hamming weight 4 is 1, 2, 3, 4, 5, 6, 7. And A5, A6 are also 0. There are no code words with Hamming weight 5 and 6. There is just one code word with Hamming weight 7. So this is the weight distribution of the linear block code. Alright, we'll move on to question 3. This question also uses the previous parity check matrix. Consider transmission of these code words whose H matrix is given in Q1 over a binary symmetric channel with crossover probability P is equal to zero point 0.1. What is the probability of undetected error? So you have this code word or code book. The set of all code words is called the code book, along with the mapping between your message to the code word. So you have your code book that is given in this table. This table is what you would call a code book. So you can just directly look at the message and see what the code word is supposed to be, or you can see the code word and figure out what message would give rise to that code word. So it's a mapping between the messages and the code words. So you have this table. Suppose you transmit one of these code words over a binary symmetric channel. What is the probability that you won't an error has occurred but you won't be able to detect it? That means there are so many errors that the code word that you sent has changed into some other code word. So suppose you send this code word full of zeros, and the first, third, and the seventh bit, there an error occurred, and an error did not occur in the other bits. Then what will happen? If there is an error, this one will change to 0, this one will change to 0, and this one will change to 0. But there is no error in the remaining zeros, so it will change to 0, 0, 0, 0, 0. Now when you get 0, 0 at the receiver, 0, 0 is also a code word, right? So you won't be able to tell whether the transmitter sent you the 0 code word and you received it without error, or whether the transmitter actually sent you the code word for 0001, but the errors happened in such a way that what you received is the code word 0. So if that happens, you can't tell that an error has not occurred. So that error will go undetected. The question asks, what is the probability of this happening? So each of these code words could change into any of the remaining 15 code words, and you would not be able to detect the error that occurs. So what we will do in this situation is we'll assume that the code word 0000 has been transmitted and you received a different code word, and you will find out what is the probability that that particular code word was received. That is, what is the probability that the error occurred in those particular bits. And we'll do that for each of the possible code words. So what is the probability that this 0 change to the code word 0 change to this code word? What is the probability that the code word 0 change to this code word? What is the probability that it changed to this code word? You will do that for all the other code words and add them all up. That will give you the probability, total probability of error being undetected. So instead of adding them like that, you can see, so what is the probability that 0 was changed to this particular code word? Since the errors occur independently in each bit, probability that this 0 changed to 1 is the crossover probability P. Probability that this 0 stayed the same, it did not change, is 1 minus P. So probability but that both the first bit changed to 1 and the second bit did not change is P into 1 minus P. So the probability next, the probability that this 0 changed to 1 is again P. So it's a multiplicative. I mean, you should have learned this in probability. So the probability that this code word changed to this code word is simply the product of probabilities, or how do you write it? P of y given x is simply the product of p of yi given xi. That is probability that you received code word 1010001 given that you sent the code word 000 is equal to the probability of product of individual probabilities. That is, you send a 1 and you get a 0, into you send a 0 and get a 1, into sending a 1, sending a 0 and getting a 1, and so on. But what exactly will this be? So whenever a bit has not been changed, the probability of that happening is 1 minus p. Whenever a bit has changed, the probability of that error occurring is p. So how many of these bits will change? So how many places will 0 change to 1? That will be equal to the Hamming weight of this code word. So if the Hamming weight is I of those bits change from 0 to 1. The remaining n minus I bits did not change. So in a binary symmetric channel, the probability that this code word changed to the second code word is p power I into 1 minus p power n minus I. Okay. And that quantity will be the same for all code words that have the Hamming weight I. So for all code words that have Hamming weight 3, the probability of error not being detected is p power 3 1 minus p power 7 minus 3 4. So when you add them up, how many times will this term get added? It will get added ai number of times. So the overall probability of error being undetected, this was the formula was given in the class. I just explained how that formula works, that's all. So the solution, probability of error going undetected, is summation of ai p power I 1 minus p power of n minus I. And this I can go from 0 to n, as we saw in the previous problem. So now they have given p is equal to 0.1. You calculated the weight distribution ai for 0 to n here in the previous problem. It's you have to just plug in the values. So here a0 is 1. Okay, you won't consider a0, you will start from 1 because what you are sending is 0000, and if you receive 0000, then there is no error, so you don't need to, there's no probability of error there when you send 0 and get 0. So what's left is a3 is 7, a4 is 7, a7 is 1. So this will be for the previous question 7 code words with Hamming weight 3. So 7 p cube 1 minus p power 4. 7 code words with Hamming weight 4. 7 p power 4 1 minus p cube. And 1 code word with Hamming weight 7, that is p power 7. You can substitute the value for p as 0.1 and calculate and verify. I'll give you the answer. It will turn out to be 5.1 into 10 power of minus 3. You can calculate it yourself and verify whether you get this value. Alright, we'll go to question 4. Now we have moved on to a different question that doesn't depend on the parity check matrix given in the previous one. So what is the correct option for the following statement? For an nk linear block code, the number of even code words is equal to the number of odd code words. So is this statement sometimes true? That is, are there a few codes for which it is true and a few codes for which it is false? Is it always true? Is it always false? Or is it none of these? What do you think? So in an nk linear block code, is the number of even code words always equal to the number of odd code words? If there are both even and if there are both even and odd code words, then it is true. But it is possible that you have only even weight code words. That is also possible. So if you have only even weight code words, then the number of even code words won't be equal to the number of odd code words. So it is only sometimes true. So there do exist codes where all the code words have even Hamming weight. So the answer is sometimes true. But you can't have any code word, any code with only odd weight code words. That is not possible. because the code word 000 has to be in the code, and that will have Hamming weight 0, which is not an odd number. And also the sum of any two odd weight code words will be an even weight code word. So if you have at least two code words, then you if they are both odd, then their sum, which is an even weight code word, should also be in the linear code. So the reason for this, there are probably different ways to prove it. uh, I'll tell you the reason in my way. Not sure if you can understand it, but at least you should get an intuitive understanding of why that is happening. So let's say, first of all, there must be, if there are only even weight code words, obviously the statement doesn't hold true. So let's check for codes which have even weight code words and odd weight code words. So let's separate the code words into two different sets. SO is the set of odd weight code words, and SE is the set of even weight code words. Okay, now take one code word from this set of even weight code words. Let's start with the odd weight ones. Take one code word with a set of odd weight code words. Okay, pick one code word. And then what you do, add it to each of the code words in the set SE. So add it to each of the even weight code words. You will get a different code word, right? Since it's a linear block code, the sum of two code words will be a code word. So you're adding an odd weight code word with an even weight code word. That will also have to be a code word. Call that set S SO prime, which is this code word added to each of the code words in the set SE. Now the number of code words in SE, when you add one odd weight code word, you can't get the same code word again, right? So if you to two different code words, if you add some other code word, you will get two different code words in the end. Okay, if you so to each of these even weight code words, if you add an odd weight code word, each of them will give a different result. So the cardinality, the number of code words in this set SO prime, will be equal to the number of even weight code words. Also, since you're adding an odd weight code word to an even weight code word, the end result will be an odd weight code word. But all the code words have to be included within these two sets, because you're only adding two code words, you can't get something that is not a code word. So all the code words in this set SO prime, they're all odd weight code words. So this SO prime, this set is a subset of SO. Right, this SO is a set of all odd weight code words. And this SO prime is a set of some code words of odd weight. And it has only odd weight code words. So SO prime must be a subset of SO. That would mean that the cardinality of SO prime must be less than or equal to cardinality of SO. And that these two. But here we have found that cardinality of SE is equal to cardinality of SO prime. So the cardinality of SE is less than or equal to cardinality of SO. That is, the number of even weight code words must be less than or equal to the number of odd weight code words. Okay. Now you do the same thing. Do the same by picking an even uh, picking an odd weight code word and adding it to each code word in the odd set itself. So here I picked a code word, added it to the code words in SE. Now pick a code word, odd code word, and add it to the code words in SO. Now what will happen? Let's call it SE prime. So when you add two odd weight code words, you'll get an even weight code word. So by doing this, whatever code words you get, they must be even weight. So this SE prime must be a subset of the even weight code words. But also, the way you got this is you took a odd weight code word, added to all the code words in SO. So the number of code words in this new set is equal to the number of code words in the odd weight set. So the cardinality of SE prime is equal to cardinality of SO. That means that this statement will imply cardinality of SE prime less than or equal to cardinality of SE. So combining those two, you will get cardinality of SO is less than or equal to cardinality of SE. That is, the number of odd code words is less than or equal to the number of even code words. Let's call this 1 and I'll call this 2. So both 1 and 2 are true. That is SE less than or equal to SO and SO less than or equal to SE. That is only possible if SO is equal to SE. 1 and 2 say that cardinality of both sets is same. So the number of odd weight code words must be equal to the number of even weight code words. That's the reason. Okay. At least that's how I would prove it. Maybe other people have different methods of proving the same result. Which question was this? Question 4. Let's move on to question 5. A linear block code is specified by the generator matrix H as given below. And the H matrix is 0, 111, 001, 101, 0101, 11000011. What are N and K? I'll give you 2 minutes to solve this. In the meantime, I'll use the washroom and come back. Alright, I'm back. Finding n is easy. N is the number of columns in the parity check matrix. So n is 7. To find out k, first you have to find out the rank of h. Let's do that. So we are allowed to rearrange the rows. We'll use elimination type of method to find the rank. We will bring it to the row echelon form. Bring the matrix to row echelon form, and the number of pivots in the end will be equal to the rank of the matrix. So we'll first exchange row 1 with row 3, keep row 2 as is, then add row 2 will change to row 2 plus row 1. That will give you 1 plus 1 0, 1 plus 0 1, 1 0, 1 1 0. Then you have to eliminate this one. For that you will do row 3 will change to row 3 plus row 2. So this is part of linear algebra. I'm just doing elimination. If you don't know, you could take a linear algebra course on NPTEL. 0 0 0 1 1 1 1, and that's it. So we have three pivots. So the rank of this matrix is rank of H is equal to 3. And here when I am doing row 2 plus row 1 and row 3 plus row 2, it's done in binary. So I am adding these two rows bitwise in binary. So you have to keep that in mind. If you simply if you confuse, if you forget that they are binary numbers and try to find the rank, you might get a different rank if you treat them as real numbers. So the rank won't be the same in the real space and in binary space. Okay, rank of the parity check matrix will be equal to n minus k. So k will be equal to n minus 3, which is 7 minus 3. So k is equal to 4. Therefore, the code is a 7-4 linear block code. Let's go to question 6. Which of the following statements is false for linear block codes. First statement is sum of two code words is a valid code word. That is a true statement. Next option is the random error correcting capability of a code is lower than the random error detecting capability. That is also a true statement. The random error detecting capability is d minimum minus 1, and the random error correcting capability is floor function of d minimum minus 1 divided by 2. So d minimum minus 1 divided by 2 is always smaller, it's is smaller than d min minus 1. So the random error correcting capability is always smaller than the random error detecting capability of a linear code. Third statement, the probability of undetected error is independent of the transmitted code word. This is also a true statement. So in the previous question here, I had explained how we get this formula for PU of E, where I started with the code word 0000 and found out what is the probability that it has changed to another code word among the remaining 15 code words. So suppose I started out with 0001, that is I transmitted 0001, and it changed to one of the other remaining 15 code words. The probability of that happening is also equal to the same quantity. Only problem in that case is you can't write a simple direct formula like this, because when you try to find the probability of zero this code word changing to the second code word changing to the third code word, when you try to find the probability of that, so 1 changes to 1 with probability 1 minus p, and 0 changes to 1 with probability uh, p, and again 1, so 1 minus p again. So in this the bits are not changing, so in 4 places it's not changing. This and this place it's changing. So the probability that the second code word changes to the third code word is 1 minus p power 4 into p cube. So this will depend on the distance, Hamming distance between these two code words. So we'll have to find out the Hamming distance with each of the remaining code words instead of the weight. So weight you can directly tell from the code word itself. Now the Hamming distance between 0 and any other code word is simply the Hamming weight of that code word. So that's why this formula is actually very simple. So the I, you can make use of I, which is the Hamming weight, and the weight distribution, AI. If you wanted to start out with the code word for 0001 and follow the same procedure, then instead of this weight, you would have to have a column with the minimum distance, and then you will have to get a minimum distance distribution from that particular code word. and then not the minimum distance, the distance between that code word, Hamming distance, and then you'll have to find out how many terms of this form are there and add them up. So at the end of the day, you'll get the same answer for all other code words, but the formula for it won't be as simple as starting out with 0. So that statement is also actually true. Probability of undetected error is independent of what you transmit. So all three statements were true. That would mean that there is no false statement. So the question asked which of the following statements is false. The answer will be option D. That was question 6. Question 7 is as follows. Both question 7 and question 8 are using the same code word. So let V is equal to 0101 0100 110 be a minimum weight non-zero code word for a linear block code. The random error correcting capability of the code is blank. So the code word is given and they're telling you that this particular code word has the minimum weight among the non-zero code words. So a fact about the linear block codes is that the minimum weight of a non-zero code word is the minimum distance. Of the code. Okay, it seems trivial, but it's not as trivial. You'll have to prove that. But I'm not going to prove it here. So the minimum distance of the code dmin is equal to minimum weight so it will be equal to the weight of the minimum weight non-zero code word. So the distance between 0 and this minimum weight non-zero code word will be the weight of the Hamming weight of the code word, right? The Hamming weight of a code word is the number of ones in that code word. So wherever a 1 occurs, it will be different from the code word 0. So the 0 code word has zeros everywhere. You have some code word that has ones in some places. So in these places, these two code words will differ. They will have different value. That is the distance between code words, the Hamming distance. That is how the Hamming distance is defined. The number of bit positions in which two code words differ is the distance between those two code words. So when you have the zero code word and some other code word, this distance will be nothing but the number of places where 1 occurs, which is nothing but the Hamming weight of this code word. So this is a distance between two code words. This could be the minimum. How do you guarantee that those two code words will be less than this? If you had some other code word with ones in some other places, how do you know that the distance between these two code words won't be less than the Hamming weight of this? That you'll have to prove it yourself. So in this question, what is the weight of this code word V? Weight of 0101 is how many ones are there? 1, 2, 3, 4, 5. 5. That means the minimum distance of this code word is 5, which means from the in the previous question I told you the random error correcting capability of a linear block code, that is the floor of d min minus 1 over 2. And d min is 5. So this is 5 minus 1 over 2. 5 minus 1, 4 divided by 2 is 2. Floor of 2 is simply 2. So it can correct up to 2-bit error. So here what we mean is that that's the theoretical possible error correcting capability. It doesn't mean that any decoding theorem, decodability theorem, or what do you call it? Any decoder you use will be able to correct two errors. You might be able to only correct one error with some decoder. So that's why designing the decoder is also important. Simply making the code is, of course, the important part is coding, but how you decode is also important, because if you are decoding algorithm, then people might not use your code at all, because they might have to pay much more if your decoding is very complex. All that so they might not use your code. So your decoder is also an important part of error correcting codes. You should understand how your decoder works. All right. Question 8. For the linear block code word is given by the same thing again, 010101000110. The maximum number of Erasures. Corrected by the code is. So an erasure is different from an error. In an error, if you sent a bit 1 and you got a bit 0, that is an error. In an erasure, you send a bit 1 but you don't receive that bit at all. For example, you might have noticed this while watching videos or making a video call or even a normal call. You'll be talking to someone, but the voice will get garbled sometimes. So you will feel like some words are not, some words are getting cut off in between. Some, you should have experienced this in while watching a video. Maybe some frames are dropping, or playing a video game, the screen seems to be stuttering a bit. So all those cases will occur when instead of an error, the frame itself or the data packet or the bit itself is not sent. So how will you know what happened in that case? The bit didn't even reach you. So how do you know what bit that is? That is called an erasure, and that's a different type of coding. It's called erasure correcting codes. I don't think we'll be studying erasure correction anytime soon. Probably not part of this course, but research is being done in that also. In IISc, a professor called Vijay Kumar, he has retired, but he is an honorary professor now. But he used to work on this erasure correction for mostly video streaming. Not sure if he is still working on that. He was working on that like 2 3 years ago. So, but erasure correction capability is similarly d min minus 1. So it is, I'm not sure if it is erasure detection or erasure correction. Uh, for erasures, it's a bit different, but okay, we'll take it as d min minus 1 for now. D min was 5, so this will be equal to 5 minus 1, 4. Alright, two more questions and we are done for this week. Question 9. Consider an, okay, coming to this, here in this previous question, I told you that sometimes this is true, right? The number of even code words is equal to the number of odd code words. For that, you can see an example right here. So in this previous example we did, having weight 3, there are 7 code words. That's an odd number. 3 is odd, right? So the weight of the code words is odd. 7 is also an odd number. So having weight 7, those are odd numbered code words, odd weight code words. So there are 7 plus 1, 8 code words with odd weight. Similarly, having weight 4, you have 7, and having weight 0, you have 1. So you have 8 code words with having weight, which is an even number. So this is an example for question 4. I forgot to tell you that. Okay. So similar to how I had proved for that question, this question 9 also has a similar proof, similar method. Consider an NK linear code. A code is labeled by the capital letter C, whose generator matrix. So the, by the code we mean the set of code words. Generator matrix G contains no zero column. So derive a relation between, of course the original question is different, they are given options, but the options is just to uh, the options are not nice to look at, so I'll just write derive a relation between d min and nk. So how is the d min dependent on the code parameters n and k? They're asking you to give a formula basically, uh, or at least if you can't find out what d min is equal to, if you can give d min is less than or equal to or more than equal to. Okay, here we'll use the same logic I had previously used. Before that, consider a so you have this code, list out all the code words in the form of a table, okay, where the code word is in the form of a matrix, where each row of the matrix is a single code word. Okay, now none of the columns of this table will be a column of zeros. Why is that? That is because this matrix G contains no zero columns. So if G has no, let's say you pick a column in G, this is your G, and this column has to have at least a single one, right, in some position. Let's say in row J it has a 1 and it has a 0 everywhere else. When you list down the code words, right, this is the code array. For some message U which has a 1 in the jth position, the corresponding code word will be, sorry, uh, yeah, how do I put it? So give me a minute, let me think on how to say this. Okay, this be let there be a 1 in row j and let this be column k. Okay, consider the kth column of this code array, that is the list of code words where each row is a code word. Okay, in C. Now there will be some message 000 with 1 only in the jth position, such that the code word for this message will be simply this row, right? So if you've seen in linear algebra, what this when you multiply a row vector by a matrix, what it is doing is taking a linear combination of the rows of that matrix. So since there is a 0 in all these positions, the code word corresponding to this will be nothing but row j of this matrix, and that will be listed somewhere in this code array. So that means there is a 1 in the kth column wherever that code word is listed. So that means if there is no column of zeros in G, there will be no column of zeros in C also. Okay, that is what I wanted to say. So there is at least a single 1 in each column of the code array C. That's the first thing that you have to know. Next, what you do is, so in this particular column K, in some rows there will be zeros, in some rows there will be ones. Pick out all the rows where there are zeros. Each row is a code word here, don't forget that. The set of all those code words, call that S0. So all the code words that have a 0 in the kth column, kth bit, are in the set S0. All the code words which have a 1 in the kth bit position, put them into set called S1. So these are all, let me write it, set of all code words that have a 0 in kth bit, and S1 is the set of all code words that have a 1 in the kth bit. Now again, consider S1 prime. The way you get S1 prime is, you pick a code word in S1 and then add it to each of the code words in S0. What will happen? Each code word, the code word in S1 will have a 1 in its kth position. When you add it to a code word in S0, which has a 0 in its kth position, you will get a code word which has a 1 in its kth position. So all the code words in this set S1 prime are actually code words in S1 because they have 1 in their kth position. So S1 prime is a subset of S1. But by adding a code word in S1 to each of the code words in S0, you will get a different code word. So the number of code words in S1 prime will be equal to the number of code words in S0. But since S1 prime is a subset of S1, cardinality of S1 prime is less than or equal to S1. This means that cardinality of S0 is less than or equal to cardinality of S1. It's a similar logic that I had used earlier. Now similarly, do this the other way around. This code word which has a 1 in its kth column, kth bit, add it to each of the code words in S1 itself and call that S0 prime. Okay, when you add a code word which has a 1 in its kth position with another code word which also has a 1 in its kth position, when you add those two, you will get a 0 in the kth position. So you will get a code word in the set S0. So this S0 prime is a subset of S0, which implies the cardinality of S0 prime is less than or equal to cardinality of S1. Now since for to each of the code words in S1 you are adding a different code word, you will get the same number of code words as there were in S1. So the cardinality of S0 prime is equal to cardinality of S1, which will then imply that cardinality of S1 is less than or equal to cardinality of S0. So 1 and 2, cardinality of S1 is equal to cardinality of S0. That means there are the same number of code words with a 1 in the kth position as there are the number of code words with a 1 in the with a 0 in the kth position. So half the code words have a 0 and half the code words have a 1 in the column k. That means in column k there are how many ones? Half of these rows have a 1. How many rows are there? There are 2 power k code words. Half of those have a 1 in column k. So there are 2 power k divided by 2. So the kth column has, okay, this might be a bit confusing. The k here and the k there are different. So let me just call this the L Lth column. I'll change this to the Lth bit. Okay. So the number of ones in the Lth column is 2 power k by 2, which is equal to 2 power k minus 1. This is true for all the columns. This logic had nothing to do with which column we picked. It will be true for all the columns. So if you count the number of ones in all the columns, total number of ones. So here L is arbitrary. That means we could have picked any column and get the same. We could pick any column and get the same result. So each column has 2 power k minus 1 ones. So total number of ones in the code table are n into 2 power k minus 1. Now remove the 0 vector from the code book you are left with 2 power k minus 1 non-zero code words, and each of their weights is greater than or equal to the minimum distance. Why? Since, as we saw in the one of the previous questions, the minimum distance is equal to the weight of the minimum weight code word. That means all the code words that are not zero must have a minimum weight which is larger than or equal to d minimum, with weight greater than or equal to d min. So what does it mean by the weight is greater than or equal to d min? The number of ones, the weight is the number of ones in that code word. So the number of ones in each code word is greater than or equal to d minimum, right? And how many such code words are there? 2 power k minus 1 code words. So the total number of ones must be greater than or equal to d minimum into 2 power k minus 1. Right? There are 2 power k minus 1 code words. Each code word has weight at least d min. So the total weight, that is total number of ones when you take all the code words together, must be at least d min into 2 power k minus 1. So we have two different inequalities equations here. If you combine both of them, what do you get? N into 2 power k minus 1 must be greater than or equal to d min into 2 power k minus 1. That means your d minimum must be less than or equal to n into 2 power k minus 1 divided by 2 power k minus 1. That is the relation that we get from this. Alright. Last question for today. It's an easy question. Let C be an nk linear code. Suppose hi1, hi2, hi6 are the 6 columns of the parity check matrix H of the linear block code C, such that hi1 plus hi2 plus etc plus hi6 is the zero vector. These are all vectors. There exists a code word of Hamming weight dash in C for sure. That is, there always exists a code word of which Hamming weight. Using only the information given to you, what can you say about this? So the parity check matrix H has these columns hi1, hi2 up to hi6. One way to rewrite this equation that they have given is this parity check matrix times the vector 1 1 1 1 1 1. If you do this multiplication, if you learned linear algebra the right way, then you will know that if you multiply a matrix with a column, then the product will be the linear combination of the columns of the matrix. So this product is nothing but hi1 plus hi2 plus etc., which is equal to 0. That means this vector 1 1 1 1 1 is a code word. And what is the weight of this code word? It is 6. So there is a code word of having weight 6 in C definitely. There might be other code words with other weights. This 11111 is also a code word. So the answer is 6. So in this way, if they give you any equation, let's say they give you that hi1 plus hi3 plus hi5 is 0, then the code word you can rewrite that equation in a similar form. So hi3, hi5 and hi3 4 5 are hi3 plus hi4 plus hi5 is 0. Let's say that's what they are given. Then you can put a 1 in those three places, 3 4 and 5, and a 0 in the remaining places. When you multiply this, you will get hi3 plus hi5 4 plus hi5, which will be equal to 0. So that would mean this is a code word. So if some columns in the parity check matrix add to 0, then corresponding to those columns you can put a 1 in your code word and a 0 in the remaining places. That will be a code word for your code. Okay, that's it for today's problem solving session. I will meet you next week.